Okay, the next speaker is Vinicius Ramos from IMPA, and he will tell us about the equivalence of Ekeland-Hofer and equivariant symplectic homology capacities.
Thank you, Leonardo. Okay. So thank you, first of all, for the invitation to speak at this edition of this workshop. So before I start my talk, I just want to say that I've been to this workshop many times. So first as a student, as a PhD student, it was actually a great opportunity, a great excuse for me to come to visit my parents. I knew that there was this conference I could come to, get some funding, and it was great to come back to Rio when I was a PhD student. And then later on, and then eventually I came to work here, and I've been very happy to participate many times. And in fact, this conference was even the origin of a semester-long program we organized here in 2019. So yeah, I've been very happy to have this as a constant conference in my life for many, many years. Yeah. So I want to tell you today about kind of a long project that Jean and I worked on for a few years, and eventually we wrote a paper, which is on the archive since last December, and you can take a look at. And it's about the equivalence of two sequences of capacities, the Ekeland-Hofer and much more recent equivariant symplectic homology capacities. So I'm going to start with a little bit of history. So I think that many of you will know a lot of the history I'll tell you, and probably some of you will be able to even fill in some details, things that I don't know or I wasn't around. Although I think that the people who were at the very beginning of all of this story, none of them are here. But anyway, I'll also tell you the stories that I heard from different people, especially Hofer. Okay, so we start with Gromov's non-squeezing. That is in many ways the starting theorem that gave birth to symplectic topology as we know it. So this was from '85. So Gromov proved the following result. So if you take a ball in dimension 2n, so let's say the set of points in Cn, such that the norm is less than or equal to r. So this is the ball of radius r, and then you take the cylinder, which in this context is a two-dimensional ball crossed with Cn minus 1, where Cn is endowed with a standard symplectic structure. So Gromov proved that in order for there to exist a smooth embedding that preserves the symplectic form, there needs to be the case that r has to be less than or equal, little r has to be less than or equal to big R. So of course, the direction where r is less than r, that the symplectic embedding exists, that's obvious by inclusion, but the theorem was that the other direction also holds. So you cannot squeeze a ball inside of cylinder of a smaller radius. So this was a big result because up to then there were no known global invariants of symplectic structures, and for another reason this is very important is because he introduced the study of pseudo-holomorphic curves into symplectic geometry. So he basically, so he introduced the technique these techniques in the 80s, and before then people were really doing like functional analysis and using other techniques, and then this was a combination of a lot of things. And then after that, as far as I understand, there were some discussions of what to do with these ideas of holomorphic curves, and but anyway, at the time, Ekeland and Hofer, and also Hofer and Zender, were discussing similar kinds of questions. And one of the ideas was a couple of papers of Ekeland and Hofer where they, sorry, but before that, I should say that one of the things that this theorem led to was the idea of how about we try to put balls inside of some other symplectic manifolds. What can we get, or what kind of obstructions can we get? And there were some of these ideas in Gromov's original paper. So I think he didn't quite say this word capacity in his paper, but he did talk about the idea of trying to find the largest ball that symplectically embeds into a manifold. So which we now call either the Gromov width or the Gromov capacity, which I can say something like this. So if X omega is a symplectic manifold, you could try to ask what is the supremum of R, or maybe, you know, as usual, we say pi r squared, such that the ball of radius r symplectically embeds into, let me write an S like this, into this symplectic manifold. Okay, so this idea was already in Gromov's paper, but then Ekeland-Hofer, kind of inspired by that, they decided to do something, and then Hofer and Zander, it's kind of at similar time, they decided to get something that is similar to this and that obstructs this kind of embedding also, but without using holomorphic curves. So using like the more classical functional analysis methods. So then Ekeland-Hofer came up with a definition and with an example of what was called a symplectic capacity. And as you probably, most of you know, there are many, many examples. But let me give you the definition that, roughly the definition that they gave in '89, which is the following. So a symplectic capacity is a map that, you know, maybe takes some subset of symplectic manifolds in dimension 2n, sometimes all of them, or sometimes like a reasonable collection, and spits out a positive number, and sometimes you allow the number to be infinity, which satisfies the following properties. So there are two main properties. I guess the first one is that it's a two-dimensional invariant. So if you take your symplectic form and you multiply it by a positive number, I mean, symplectic form is a true form, you multiply it by a number, this will scale with this number for a positive number r. And then the second property is that it obstructs symplectic embeddings. So if x1 omega 1 symplectically embeds into x2 omega 2, then the capacity of x1 omega 1 is less than or equal to c of x2 omega 2. And then usually we require a non-triviality condition, otherwise you can just take the function 0 or the function infinity, and it's kind of not interesting. So usually you require that the capacity of the ball is positive, and the capacity of the cylinder is not infinite. And then, yeah, those are the usual assumptions. And I think originally, on the first paper, the Ekeland-Hofer also required that these two are equal. And that's what we call a normalized capacity. So, I mean, let me say for the same R. So, you know, if these two are equal, if you require these two to be equal, then you say this is a normalized capacity. And so there was already some talks about, I mean, Alberto mentioned this a little bit in his talk, but I'm not going to talk too much about normalized capacities in this talk because I want to talk about the whole sequence. So on the second paper of Ekeland-Hofer, I think this was that was published in 1990, they defined, so Ekeland-Hofer in 1990, they defined a sequence of capacities. A sequence of symplectic capacities for subsets of R2n. Okay, so this sequence I'm going to call in this talk C1 EH, C2 EH, and they are non-decreasing, like similar to the sequence that Michael was talking about earlier. But in this case, they're defined in every dimension, but only for subsets of R2n. Okay, and I want to just tell you, I mean, a couple of calculations. So they in their paper, I'll give you the definition in a little bit. It doesn't use holomorphic curves, but it uses some non-trivial functional analysis and index theory. But I just want to tell you that two calculations that they did for two classes of manifolds. So they're very hard to compute in general, but they computed them for ellipsoids and for polydiscs. So let me remind you that an ellipsoid, a symplectic ellipsoid, you only need n parameters in Cn. So I'm going to just use the usual normalization, which is you consider the set of the vectors in Cn such that pi times the norm of Z1 squared over A1 plus the norm of Zn squared over An is less than 1. And then you can also define the polydisk, which is the symplectic product of n disks. So this is the set of Z1 through Zn in Cn such that pi times the norm of Zi squared is less than Ai. Okay, so these two examples, they computed in the original paper these capacities for these two examples. So in the example for the ellipsoid, this is basically the kth term in the sequence. So basically you take all of the multiples of Ai for all n a natural number, and for all the i's, for I from 1, no, ki. For k a natural number and I from 1 to n, and then you put them in increasing order or non-decreasing order, and then you just count you take the kth element. I guess, yeah, so natural numbers starting at 1. Okay. So basically, these are the lengths of all the Rabe orbits on the boundary here. Yeah. Okay. So and then the ck of the polydisk, it's kind of funnier in some ways. I mean, this is kind of very reasonable, but the Ekeland-Hofer capacity of the polydisks, this is basically you just need to look at the smallest one of these and take the multiples of the smallest one. So this is just k times the minimum of A1 through An. So it's very crude in some sense, because you really don't see the other numbers that are bigger than the minimum one. Okay, so they computed all of this, and this is very cool because, first of all, it already recovers Gromov's non-squeezing. So you see that in particular if you look at C1 of that ball, it's equal to C1 of the cylinder, which you can compute by taking the limit as all of the other ones go to infinity except 1. These are going to be the same, and this is going to be pi r squared. So in particular, just the existence of these reproves Gromov's non-squeezing without holomorphic curves. And so the C1 Ekeland-Hofer is a normalized capacity. Okay, but then you can start playing with them, and you see that sometimes sometimes they give you sharp bound. For some other embedding problems, they give you sharp bound. So I'm just going to give you one simple example for those who haven't thought about this. So say that you want to embed P11 inside of the ellipsoid EA2A. So this is, you can also do it for the ellipsoid EAA, but that's simpler and you can do it with other capacities. But in this case, Ekeland-Hofer actually is the right one to use. So if you look at if you put on your toric glasses, the picture you see is you're trying to embed P11 into an EA2A. And if you just apply these formulas that I gave you, in this case, the capacities will be 1, 2, 3, 4, etc. So this is the sequence of capacities. And in this case, the capacities will be A, 2A, and then 2A appears twice, because it appears as twice this A and once this 2A. And then it keeps going. And it follows from the second property of capacities that using the C3, so the third one, if this one embeds into this one, then the 3 has to be less than or equal to this 2a. So it implies that a has to be greater than or equal to 3/2. And with some very basic analytic geometry, you can see that for this exact a, for a equals to 3/2, the square of side 1 fits in here. So the Ekeland-Hofer capacities tells you can't do any better than this, but you see that you actually can do that by just inclusion. So then that means that Ekeland-Hofer capacities are sharp for this particular embedding problem. Okay? I mean, this is just one example. I mean, they don't work generally. I mean, sometimes they give you the sharp obstruction. Many times they don't, which is why we need many other capacities. ECH capacities. Now we have these elementary capacities, and then there are many other things, like, but a bit out of the scope of this talk. Yeah, so I should say that you can't get that from ECH capacities, for example. But Michael is very tricky. He didn't like that, so he ended up finding some other holomorphic curves in ECH that are not captured by capacities, which he called the beyond ECH capacity. And then they do find that. So if a capacity, ECH capacities are not enough, you can keep digging for holomorphic curves, and then they'll a lot of times give you what you want. Okay, so this is the story back in the 80s, and then as I was talking to Hofer, he basically said that Floer had mentioned something about these capacities coming from some kind of Floer homology, and he gave a talk at MSRI in 1988, which I'm going to quote. So this is something that was from a talk, and it was a quote from the notes of Alan Weinstein. So I don't know exactly if it's correct word by word. It wasn't recorded. But apparently he said, the Ekeland-Hofer capacities must come from some type of S1 equivariant homology. And maybe this will be clearer after I give you the definition of the Ekeland-Hofer capacity. So he said that, and I think, Helmut told me, and I think he told the same thing to Jean recently, that I think Floer said that he knew how to do it. Or he had, he basically said, oh yeah, I know how to do it, I'm going to do it. And then, he did a bunch of things, proving the Arnold conjecture in many settings, and he created what we call Floer homology. And I think there was never a preprint or like a complete idea of this. And there wasn't even like a full definition of what these capacities coming from some kind of Floer homology would be until like much, 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 much later. But anyway, this is kind of the idea of this paper, is to kind of fulfill this dream or this, this idea of Floer that unfortunately he didn't leave written for us. So maybe, if he had lived a few more years, he would have proven this in the early 90s. But anyway, we had some work to do, and that's what I'm going to tell you about today. Okay, so the idea is that Floer, as many of you probably know, Floer created this way of looking for periodic orbits by using a homology. And his idea was, let's try to do Morse homology for the action function. But then he was like, okay, it's kind of hard to do this, to make the analysis work. So he decided to do things, and I'm not exactly sure why, but he decided to do things in an L2 setting, in which case the gradient vector field didn't have a well-defined flow. But then he kind of wrote down this, the equation of the flow, what would be, and then he's like, okay, this is a PDE, let's study solutions of this PDE with bounded energy, and then he managed to prove the Arnold conjecture in many settings. And then after that, people used those ideas a lot to do many things. But in this particular context of R2N, this homology is usually called symplectic homology. And Victor mentioned some of that in his talk. So basically the story is like, he has this Floer homology, which I'm going to also review in a little bit, which in this open manifold setting is usually called symplectic homology. And then, basically, if you try to capture some kind of the same information, if you try to get those numbers, then you're really led to what we usually call S1 equivariant homology. Because, again, as Victor reminded us, S1 equivariant homology. So as Victor reminded us, sort of like for a Rabe orbit on the boundary of a domain, you have this S1 family of orbits. So if you just do the standard thing, you'd get two orbits, like the check and the hat. So if you want something that just kind of counts one Rabe orbit at a time, then either you kind of do the contact homology idea, which is kind of the most natural thing you would do, but has a lot of hard transversality issues, or you do the thing that seems more complicated, but is much easier to prove everything, which is kind of introducing this S1 invariant idea. So the S1 invariant symplectic homology. And kind of if you want to throw away the critical points in the interior, you do positive S1 equivariant symplectic homology. Okay, so it's a very long name. And then from that, Jean and Michael managed to find some spectral invariants. So this is Good and Hutchings, and I think the paper was published in 2019. So they finally, in many ways, fulfilled this dream of constructing spectral invariants from the natural thing from Flo's original idea, which they called the contact homology capacities, which is the CH is kind of a tricky name because they really don't use contact homology. They use positive S1 equivariant symplectic homology. Okay, so some people, they deform this C into a G and they call it the Good-Hutchings capacities. So, okay. And there are many nice things about it. One is that this is a theory that is relatively low carb on index theory. So, but I mean, in other words, it consumes a lot of holomorphic curves and some other things. So I'm not sure what the trade-off really is. But anyway, for us in the Floer homology, people who are used to Floer homology and holomorphic curves, it's probably easier to understand them than to understand the original definition of Ekeland-Hofer. But anyway, yeah, so they define this, and then one big advantage of these capacities is that they are much easier to compute. So with the technology that was developed for understanding toric domains, for example, you can compute, so they compute, Gut and Hutchings compute, so they compute this capacity for the ellipsoids, polydiscs, and much more. So they actually compute this for any concave or convex toric domain in any dimension. So basically, this is a much, much easier invariant to compute with the technology that we have nowadays. So it's very nice. So the theorem that we actually proved is that, so if you look at all the examples that are computed, so for example, ellipsoids and polydiscs, these capacities coincide. So what we proved that this is always the case for, at least for star-shaped domains in R2n. So if X is a star-shaped, so this is theorem that Jean and myself from last year. So if X is a star-shaped domain in R2n, then the Ekeland-Hofer capacities and the positive S1 equivariant symplectic homology capacities, or the Good-Hutchings capacities, coincide for every k. Okay. So for the rest of the talk, I'm going to try to explain the main ideas in the proof. And also, I'll try to give you the definition of both of them. But before that, are there any questions? Okay. So let me define the Ekeland-Hofer capacities. Capacities. So they're defined in a setting that is probably very standard to the people doing analysis, but to non-analysts, it's maybe not something we're so used to, but it's these fractional Sobolev spaces. So the space that's relevant is what I'm going to call E, is a Hilbert space, which is called H1 half from S1 to R2n. So this is a subspace of L2, where you basically require the function to have a half derivative. But I mean, that makes sense when you look at the Fourier series of the function. So this is basically the set of curves. So x is a function that I'm going to write with its Fourier expansion. So this is a curve in L2 from S1 to Cn, such that a certain series converges, and that's kind of like basically a half derivative. So such that the series of norm of k, or the absolute value of k, and the norm of x to the k squared converges. So those of you who haven't seen this, I mean, to require it to be in H1, then you'd want the derivative to be in L2, which would mean that when you put a square here, then you're in L2. So anyway, this is kind of the square over 2, which is why it's called H1 half. Okay, so that's the setting. And anyway, then you have a norm, which is going to be basically the norm is going to be less than infinity if and only if x is in this space. So the norm in H1 half is, so this is the norm for something in L2 which has a Fourier expansion. So this is the, maybe let me remove this and let's just leave the norm like that for spaces of functions. So this is the absolute value in Cn. So this is the norm in Cn, and then plus usually people put a 2 pi here, k times norm of k squared. Okay, so this is the norm in H1 half. And I mean, I'm not an analyst, so it's hard for me to give a lot of analytical insights, but I think that part of the reason that this H1 half space was so good is that when you look at the action functional, which is the functional that detects orbits of the Hamiltonian vector field, that the action functional, the gradient here has a well-defined flow. So I'm not sure if that's the only reason, but it's definitely one reason why this H1 half setting was very popular, at least by Hofer and collaborators in the 80s. Okay. So now we want to do things for what are called admissible Hamiltonians. So because our manifold, which is R2n, is open, we have to be a little careful about the behavior of Hamiltonian at infinity before talking about the Hamiltonian flow and Floer homology, or even before Floer homology in this setting. So we're going to say that H is admissible. So H is a Hamiltonian. So some function from R2n times S1 to R. So we're going to say H is admissible if, and this is something very similar to what's usually done in symplectic homology. So we want the support of H to be compact. We're going to put a slightly, funny condition, which is that we want the boundary of the support to be a smooth manifold. So we don't want it to be completely crazy. And then we want it to be quadratic at infinity, which is the same condition that Victor mentioned about it being linear at infinity. So this is something maybe confusing to the students, that quadratic at infinity with the norm in R2n is the same thing as linear at infinity with the symplectization parameter. But anyway, I just want to say that if you're a student and you haven't thought about this, maybe you want to do this calculation. But so there exists some R0 and some A, such that if the norm of x is less than R0, then h of xt is going to be equal to a norm of x squared. I mean, here, I guess, yes. So there I'm using x for a curve, and here x is a vector. Maybe I'll say z to be less confusing. Bigger. Thank you. Yeah. So outside of some ball, then the function is quadratic. And I guess sometimes people require the A to not be in the spectrum of the boundary, but I'm not going to put this condition right now. I think it's actually not necessary for the capacities, but it's, I guess, necessary, or it makes it easier to prove the theorem. I mean, it's easier to talk about symplectic homology when you already know the boundary of the support is smooth. Yeah, maybe this condition, is not. Sorry, yeah, this second one. Yeah. Okay, so now comes the index part. No, it's actually equal. Here it's equal. So you wanted to have this specific behavior at infinity. Yeah. Yeah. Sorry, you're right. Yeah, that's what we need to not be in the spectrum of the ball. So yeah. So you need A to be different from to not be contained in pi times z. Yeah. Yeah, you're right. So there's some resonance. Okay, so now comes the index theory part. Before that, let me just remind you there's the action functional, which is something that's been defined for like a smooth curve, can be extended to the h1/2 setting. So the action functional for a smooth curve is usually given by the integral of lambda, the standard primitive, over x minus the integral of x of h of t dt. This is, I guess, it's been known for a long time that this is the setting, the actional whose critical points are precisely the closed Hamiltonian orbits. And this, for the smooth case, that makes sense. And then if you want to extend this to the h1/2 case, you actually just do a little calculation to see that this extends as a functional to the h1/2 case. And in that case, this term here actually can be written as 1/2 of the norm of the projection of x to the positive space, and I'll explain what this is, minus the norm of the projection of x to the negative subspace, h1/2 squared. Okay, and this p plus and this p minus, it's basically given when you can take a decomposition, an orthogonal decomposition of E into 3 Hilbert spaces, which are basically the spaces of positive, 0, and negative Fourier frequencies. So the E plus, E0, and minus are basically the spaces where you don't have, where in the Fourier decomposition, you only have positive k, negative k, or 0k. So, I'll write E plus, and the other ones are kind of obvious. So this is the set of x is of the form sum of e to the 2 pi I k t xk for k positive. And then the same thing for 0 and for negative. So this is an orthogonal decomposition. And then you have the orthogonal projections from E to E plus or E minus, where you just throw away the negative frequencies or the positive frequencies. Okay, so if you do a little calculation, and it's not very hard actually, it's easier than it looks, then you can actually prove that this, the contact part of the action is just given by this formula. Okay, and actually already from there you can see you can compute the gradient. So from the norm in h1/2, gives you an inner product in h1/2, which I won't write all the details because it would take too long. but you can compute the gradient, and you can see that the gradient of this functional in, the gradient with the metric, with respect to the h1/2 metric, this will just be equal to p plus minus p minus, and then basically you have what's called J star of the gradient of h. And this J star is like a compact map that goes from L2 to h1/2. It's basically the induced map by the inclusion. And it turns out to be a compact map, which is very important for the theory. But anyway, I don't have time to tell you about all the details, but you can already see that this is actually a very nice vector field. And this vector field, you can actually see that there's a flow. I mean, basically, it's linear plus a compact thing. So it's like a linear vector field plus a linear part. You can actually solve it, even in this Hilbert space setting. OK. So now, to continue the definition, I need to tell you a little bit about the index theory, which is necessary. So if you take X subspace, a subset of E, so you take any subset of this Hilbert space, which is S1 invariant, then we can compute what's called the equivariant homology. So this is something that's kind of classical topology, but maybe not as well known as maybe it should be. But anyway, this is something that generalizes the case when S1, when you have a free action on X, and then you take the quotient, and you look at the homology of that. So when the action is not free, you can do something that still encompasses an invariant that encompasses the action in there. And this is basically what you have when you look at.
What is E there?
E is my Hilbert space. It's like the space where I'm doing the analysis. Yeah, so you take any subset of this space, then you have an equivariant homology, which is basically you look at the fiber product of this with ES1 over S1, and you look at the homology of that. So this, as you probably know, if X is free, if the S1 action is free, then this is the same as the homology, the cohomology of the quotient if the action is free. Okay. And the thing about this is like you can actually see some kind of dimension of X. And that's the reason why this index appears. So I mean, the formalism is slightly cumbersome, but I'm going to tell you regardless, which is the following. So if you have this S1 action, you can you actually have a map from this fiber product to BS1. And that's just a classifying map of this, and then that gives you a map from the cohomology, and BS1 is CP infinity. So this gives you a map from the cohomology of CP infinity to the equivariant homology of X, which I'm going to call, if this map is F, then this will be F star. And now I can tell you what the Fadel-Rabinowitz index is of a subset, of an S1 invariant subset. It's measuring some kind of dimension of the space, and what you want to do is you want to take the generator of this, so this cohomology ring is a polynomial ring with one generator, which is the generator of H1 of CP infinity, and you want to know how many powers of that are non-zero in the equivariant homology. So that's what's called the Fadel-Rabinowitz index. So the Fadel-Rabinowitz index is the maximum of K, such that when you look at, let me say this is Z of a generator U as the cohomology ring. So it's the maximum such that when you look at U to the K minus 1 and you look at F star, you get something non-zero. So that's the Fadel-Rabinowitz index. This stands for Fadel-Rabinowitz. CZ, right? Yeah, or TZ. No, TZ. Thank you. Okay. So for example, maybe kind of an example to inspire us is if you take if your X is a vector is a subspace, a complex subspace minus the origin. So if V is a complex subspace, so you can perform this thing here, and you can see that the equivariant homology of V of X, this will be here the S1 will act freely, and then basically we get that this is the same as the cohomology of C to the K minus 0 quotiented by S1, which will be the polynomial ring of U modded by U to the K. So in this simple case, you get that the Fadel-Rabinowitz index of this X is precisely the complex dimension, this K. So the complex dimension of V.
Sorry, Vinicius, so X is a subset of this H1 Howard. And now you're telling me that X is a vector space minus the origin contained in CN.
Oh, I'm sorry. So this is, you're right.
That's my question with about the E.
Yeah, so I'm sorry. This definition doesn't require X to be a subset of E. It just requires, it's a definition for any S1, any space with an S1 action. The definition of the Fadel-Rabinowitz index. So yeah, so I don't need this for the definition. This is true in any context. So I was kind of giving you a finite dimensional example of the Fadel-Rabinowitz index. But yeah, thank you for the question. I'm sorry for the confusion. So I guess I will say that this is a space, an S1 space, a space with an S1 action, any space with an S1 action. But I will apply this definition for subsets of that Hilbert space that have the natural S1 action, because they are spaces of functions from S1. So the action of S1 here is just rotating the circle, the domain. Okay? All right. So now I can give you the definition. And now there's one more index, which is actually, so this is relatively standard functional analysis from the 80s or maybe 70s. But then Ekeland-Hofer they figured out how to cook up an index of this that has to do with Hamiltonian orbits. And it's what I guess they just call the index in their paper, but I guess we'll call the Ekeland-Hofer index. So the Ekeland-Hofer index is the following. So given a subset, so now I actually really want a subset of, now I really want a subset of my Hilbert space. So, this is H1 half of S1 R2N, which is S1 invariant. And what they realized is like for good spaces where you actually want to do a min-max theory to get invariance, what you need to do is you want to intersect the spaces with the unit sphere in E plus. So what they want to do is they want to compute this Fadel-Rabinowitz index of the intersection of X with this S plus. I don't know how to give you a lot of motivation except that they have this idea and it works. So I think maybe if you're doing analysis at the time, then everything made sense. Maybe Alberto has a deep insight. But anyway, the idea is you have this space and you intersect with S plus. I'll give you an example later to show you that's good. And they realized that this space here for the good spaces where you want to do mini-max of the action functional, this intersection will have a good Fadel-Rabinowitz index. But more than that, yeah. No, what? No. I will put more things. So first of all, you realize that you intersect with S plus, and that will give you for the kind of good X's, that will give you meaningful information. But you actually need to be able to perturb this space. Like you actually usually want to take flows of this X, and you want to see kind of how small this Fadel-Rabinowitz index is. And then what you do is basically you allow for deformations of this x, and then you take the infimum of this for h in some space of transformations gamma. So this is kind of technical, but this gamma is some group, and I'm not going to tell you all the things, but it's a group of homeomorphisms of your Hilbert space E. And the idea is that this group, it encompasses all of the truncated gradient flows of action functionals. So this group includes the truncated flows of minus the gradient of AH for all H's. So anyway, so this is the kind of the index that they use. Are there any questions about the definition?
What is S plus?
S plus is the unit sphere in E plus. So this is the unit sphere in E plus. So let me give you an example. This is a proposition in their paper. The example is if you take a finite dimensional subspace of E plus and you sum E0 and E minus, that's something that's going to have a finite Ekeland-Hofer index. It's going to be exactly the complex dimension of this finite dimensional space in E plus. So the example is, so if you take some V, which is a finite dimensional complex subspace of E plus, and then you look at the Fadel-Rabinovitz index, the Ekeland-Hofer index of E0 plus, no, E minus plus E0 plus V, the dimension of this, or the Fadel-Rabinovitz, sorry, the Ekeland-Hofer index of this is exactly this dimension of V. I mean, what you can see here is like if you take this and you just intersect this with a unit sphere in E plus, this is going to be a sphere in this space, which has dimension, I guess, complex dimension given by this dimension. So when you do that, then it's going to be easy to see when H is the identity. But the point is that even if you change H in this complicated group of homeomorphisms, you can't go below this number. So this is some kind of index theory to prove that this infimum is going to be exactly attained by H equals the identity. Okay, so now I can define the Ekeland-Hofer capacities. So the Ekeland-Hofer capacities is now basically I just do a minimax using these kinds of subsets. So, so the Ekeland-Hofer capacities of an admissible H, so here I take an admissible Hamiltonian, is going to be the infimum of, so I look at all of the sets Xi, I look at the supremum of the action functional over all of Xi such that the index, the Ekeland-Hofer index, is at least K. So this is the procedure. And that's what's called the Ekeland-Hofer capacities. And then they can prove using some mountain pass lemma that this is always attained by, this is always the action of a Hamiltonian orbit. So this is kind of a point is that this is, so in other words, this is spectral. This is the action of some orbit. So this is the Ekeland-Hofer capacities of a Hamiltonian. And then after that, if you want to get the Ekeland-Hofer actual capacities of a domain in R2n, you have to take the infimum of those for all of the admissible Hamiltonians whose support is contained in the domain. But I'll spare you from that because I'm running out of time and that's relatively standard. It's the same thing you do for symplectic homology. Okay, but are there any questions about this definition? Xi is it's one of those x's. I just didn't want to call it x again. Xi is an S1 invariant subspace of E. it's one of those things that I just defined the Ekeland-Hofer index for. Okay. So this is the Ekeland-Hofer capacity. So I'm going to quickly tell you about the Good-Hutchings, or the contact homology capacities. So now, Good-Hutchings, much later, so in 2019, they defined some capacities coming from, oh, I forgot the T, coming from symplectic homology. And here the setup is very different, and maybe more people are more familiar with the setting, even though it's much more recent, which is, I mean, given a Hamiltonian, an admissible Hamiltonian, you do Floer homology. So what's Floer homology? It's some homology theory that's generated by the orbit. So this is a homology theory generated by periodic orbits of the Hamiltonian flow of H. And then the boundary is counts solutions to a certain PDE. So this is basically the L2 version of trying to do the gradient flow. But it's not a flow, as I told you earlier, but basically the differential counts solutions to, so maps like this, R times S1, to maybe your R2N, such that ds du ds plus j du dt minus the Hamiltonian vector field is equal to 0. And that converge to the orbits. So this is kind of standard. I think that probably most of you know this. And I mean, the actual symplectic homology, you do this for a specific slope, and then you make the slope go to infinity. But actually, the theorem that we can prove, we can fix the h, and we can fix the slope, and we can prove something. So we actually don't need to take the slope to go to infinity for the kind of the core of the proof. Okay, so then we looked at this and we're like, okay, there are these capacities, there's this Floer homology, and how do we relate them? I mean, I guess I didn't tell you how they constructed the capacities, but the capacities are basically a spectral invariant of this theory, which is basically, you compute the homology and you say the homology is basically Q for every generator, for every basically index or every even index. And then the capacity is what's the smallest action that you need to be able to generate that guy. So it's kind of a standard, relatively standard thing in homology theory. I mean, of course, every setup is quite hard, and there's this S1 thing going on, and I don't have time to tell you all about that. But when you stare at this and you're like, okay, how do I look at these spectral invariants coming from Floer homology, and how do I relate them to this? And then you see that there's actually one missing thing, which is that these look, if you can find a homology theory whose spectral invariants are these Ekeland-Hofer capacities, then you could try to connect these with the Floer homology. And that's basically what we did. So we realized that in 2000, so the proof basically has two elements. So the first one is finding out an appropriate homology theory whose spectral invariants are the Ekeland-Hofer capacities. And that's kind of something that Floer said should be done with Floer homology, but I guess he didn't kind of finish the work, so we don't know exactly what he had in mind. But what we basically came up with, we realized, is that there was a theory, a very nice method of Abondandolo and Meyer from 2005, so relatively old paper, where they actually say that you can do Morse homology directly in this space E. So I think somehow this was a paper that people didn't work on that so much, but it's actually kind of amazing that if you're not scared of H1/2 and you do things in the H1/2 setting, you can actually do Morse homology all the way. So this flow exists, and I mean, there are some technicalities, but you basically can develop a Morse homology. So not Floer, it's actually genuine Morse homology. Your critical points are the zeros of the gradient, and the trajectory and the differential is counted by intersecting unstable and stable manifolds. And so you do have a Morse homology in this setting. And of course, they didn't do it like that, but we can actually put an S1, we can do it in an S1 equivariant way. So we get this Morse homology. So, and such that the Ekeland-Hofer capacities are the spectral invariants of this, or whose spectral invariants are the Ekeland-Hofer capacities. Which kind of makes a lot of sense when you think about it, because this is something that's really in H1 half, in some H1 half space. So it makes sense that this works. I mean, there are many details, so it's not obvious. It took us a while to figure out how to do it, but it works. And then the second step is to show that this Morse homology is actually isomorphic to Floer homology. So, so then we show that the Morse homology is isomorphic to the Floer homology. I mean, again, like S1 plus, basically. And this is actually true already in the chain level. So it's actually a very strong, nice result. That if you do this Morse homology in the H1 half setting, the generators are the same, but the differential is quite different, because here you count solutions to the Floer equation, and here you count like genuine gradient flow trajectories. But it turns out that the chain complexes already are isomorphic. And this is something that we learned from a former student of Alberto, I think Michael Hecht, in his thesis. He proved the same thing, but for Hamiltonians on a torus. So we looked at his idea and we realized that it also works for Hamiltonians on R2n. Oh, I'm sorry, yeah. Oh, I thought he was your student. Oh. Okay. Yeah, so anyway, so these are the 2 points, and I'm almost out of time, so I don't have that much time to tell you very much, but I want to just say a few words about the second part, because I think it's quite nice, which is kind of how you go from the Morse homology. So this Morse homology, I mean, it's really the same like Morse homology in finite dimensions, but there is one little caveat, which is that maybe the reason people kind of gave up the H1 half and went for L2 is because of Sobolev inequalities. And it's because when you're trying to do the Banach manifold setup to try to do these things, if your tangent space is not R2n, so if your manifold is not parallelizable, then I think maybe you have a problem with continuity, like you don't know how to prove things are continuous. And then like in a more general, like if you're trying to prove the Arnold conjecture for a general symplectic manifold, maybe you can't make this H1 half method work. But if you are in a parallelizable manifold, in particular in R2n, you actually can do this. And so basically you have your space, which is this H1 half space, and then you have your function, which is the action functional, and then you just do Morse homology. So you look at the critical points, which are just the zeros of the gradient. Of course, everything with the metric in H1 half. And then it's a little complicated because when you look at the unstable and the stable manifolds of P and Q, these are all infinite dimensional, but they actually are manifolds. So you can prove that the flow is well defined. So these are infinite dimensional, but they are manifolds, Banach manifolds. And you can prove that their intersection is actually finite dimensional. So you can prove that the intersection, HU and HS, is a finite dimensional manifold. And the dimension is precisely the difference of the Collins-Zander indices in this setting. So you kind of won. So it's exactly the dream, in a way, that we teach in Floer homology classes. That's what we would like to do. But in this case, we actually can do if you do things in H1 half. So, And then, of course, as usual, you look at the index difference 1, you have the R action, and then everything kind of works well. And just to say a few words about this, the isomorphism, I mean, you get the isomorphism by defining a chain map, which is something that interpolates from the Morse homology, the H1 half Morse homology, to the Floer homology. And so how do we define this map that goes from the Morse complex? And I'm going to, of course, not mention the S1 invariant equivariance, but you can do this in the non-equivariant and also in the equivariant case. So how do you go from the Morse homology to the Floer homology? So you do that by counting what are called hybrid curves. So these are, so say you take P and Q, which are critical points. So first of all, you see that the generators are the same because they are exactly closed orbits of the Hamiltonian vector field here and there. So what's different is the differentials. But anyway, so you take two critical points of AH, so two periodic orbits of the Hamiltonian vector field. And now you define what's called a hybrid, what we call, I guess hashed called the hybrid moduli space. And this is the space of maps. So from P to Q, this is the space of maps from a half cylinder times S1 to R2n, such that this satisfies Floer's equation minus xh. And then the limit when s goes to infinity of u of dot t, this is y of t. And it starts from the descending manifold of x. So, and u of 0 dot is in wu of x, of p, sorry. Oh, p and q. P and q. So in other words, I mean, let me draw the picture. So if this is p, you draw your unstable manifold of p, and then here's q. So you want some Floer trajectory that starts from the descending manifold of p, from the Morse homology sense, and ends in q. So this blue thing is not a Morse trajectory, but this is a Floer trajectory. Okay, so there's some work to make sure everything works and the analysis is all correct. And this is in the paper if you can look up if you're interested. But sort of this is the main idea. And because this decreases action, and you can show that if p is equal to q, there's exactly one trajectory, then we see that this phi is basically an upper diagonal matrix with ones in the diagonal. So that's why this is already an isomorphism on the chain level. Okay? So anyway, this was, apologize, it was kind of a technical talk, but I hope that you enjoyed it and you got something out of it. Thank you.